Hot dog, we're expanding the brand. This is our first video on multivariable calculus, and we'll be kicking things off with a little bit of extreme values. How does a function of more than one variable find its largest and smallest points in a given region in space? So we're going to define some function xy in a region. We'll call it R. It's a good name for a region. And we're going to contain a specific point A, B. So A, B is just an ordered pair. It's the coordinate of some point that lives inside that region. It turns out that the function f of AB at that point is a local maximum if the value of the function at that point is greater than or equal to every point around it and some small disk centered about the point. So we'll say in an open disk centered at A, B. So in other words, if I pick a point, if I draw a little circle around that point and every other point within that circle is less than the function at the point I've chosen, it's a local maximum. We can also define the converse of that, the local minimum, if the opposite is true, if every point around in a little region is greater than my point. So if f of b, a and b, is less than or equal to the function around it. So we define a local maximum and a local minimum. It's a similar definition to what we did when we did one-dimensional functions. But now we kind of have this, imagine this landscape. This is a 3D function now, so this has kind of like some, roundness to it. Think there. This here would be a local max. It's the peak. At this point, if I draw a little circle around there, we can see that every other point, if I take a little step in any direction from that peak there, I will, arrive at a value of the function lower than where I started. That's a local maximum. Down here would be a local min. No matter, I draw a little disk around it. No matter where I go, I end up higher than the plane of that disk. So every point around there is higher than the point at AB. That would be a local minimum point. We can also, in this new three-dimensional world, this looks like it's a local min, but, if I look at the contour here, it turns out that if I take a step to the left or the right, I end up going higher than I started. If I take a step kind of out or into the page, into the sort of the z-axis that we can't see on the paper here, but if I kind of go this way along the curve, I find that those points are lower. And so there's a new option for a critical point called a saddle point, where it sort of behaves like a local min in one direction and a local maximum in the other direction. So now the trick is, how do I figure out where these extreme values occur? Given a function, where can I find these extreme values? Where are these local maxes or mins or saddle points? When we did functions in 1D, I could always find the critical points by looking at the first derivative. So in 1D, I have my random function, like so. We could identify these critical points because they are places where the slope, the tangent line there, would be 0. There's a transition from going to a positive slope to a negative slope or vice versa, and so that transition has to be a place with 0 slope. So we looked at where the first derivative of the function is equal to 0. Now we have more choices. Now in this 3D landscape, we can look at the rate of change in the x direction and the rate of change in the y direction, and it might be different. In order to guarantee that we have some sort of critical point, we need both partial derivatives, partial in x and partial in y, to both be 0. So we call this result the first derivative test. Basically, it says if the function f of x and y has a critical point at some point AB, and its partials exist, so we need the derivatives to be well defined, then the partial of x with respect to x at a and b equals 0, and both of these need to be true. The partial with respect to y at that point also equals 0. So we can find the critical points of a function in x and y by looking at its partials and finding what values a and b make both of them 0. We need both of them to be reaching this kind of like zero slope regime to say that there is a critical point there. So let's see how that works. Let's try an example. So we want to find the extremes of the function f of x equals x squared plus y squared. Well, we can take the partials with respect to x, so f sub x, the other partial notation there, that's just going to be equal to 2x. Fy is going to be equal to 2y. We set these equal to 0, and we find that both of these are solved when x is equal to 0 and y is equal to 0. So our point AB, where this critical point occurs, is, AB is equal to 0, 0. It's the origin. How do I figure out what kind of point this is? Well, luckily, this function kind of has a special structure. At 0, 0, the function itself is equal to 0. So that is either a max or a min, or maybe even a saddle point here. I got to think about this a little bit. X squared plus y squared. No matter what values I have, since they're squared and they're being added together, I can only ever get positive values. So if this critical point is 0, I take a step in any direction, get a new x value and a new y value, the result of the function is going to be a positive number. So, f of xy is going to be greater than 0 for all x and y not equal to 0. So that means that our point here, the origin, is a local minimum. Any other point is going to be greater than 0. So that's one example. We can try another one, but we'll switch it up a little bit. Now we'll get f of x and y is equal to y squared minus x squared, switching it up with a minus sign. Our partial derivatives are going to look basically the same. We're going to get fy equals 2y, and f sub x equals negative 2x. Again, the only place that these are both equal to 0 is the origin. This will be equal to 0 when y is 0. This will be equal to 0 when x is 0. So basically, we have a crit at 0, 0. We can examine the structure again to kind of get a feel for, what sort of critical point this is. And we see if I set, y equal to 0, we're only going to get negative values. If I set x equal to 0, we only get positive values. So the fact that there's no clear cut, everything is greater than the origin, everything is less than the function at the origin, we get a little bit of both depending on which path we take, whether x is 0 or y is 0. And so that kind of hints to us that this is a saddle point. Now that was great. We definitely were able to figure out what kinds of critical point each of these, functions had at the origin, but it turns out we were able to do that because the structures of the function were nice. That is not always going to be the case. And so we need a way to figure out, in general, what kind of critical point did I just find? How can I determine what the critical point is going to be? And that gets us to the second derivative test. So the first derivative was not enough. First derivative, generally not sufficient to determine nature of the critical point. Well, enter the second derivative test. So we need, again, the second derivatives to actually exist. And remember, there are four of them. We can take, the partial with respect to x, and then either the partial again with respect to x or with respect to y. And then the same thing with y going into x and then y again. So if all second derivatives exist, and we have found a place where the first partials are both 0, then we can classify that point as a local max at our point AB if the double partial of x is less than 0 and the product, this is going to be a weird quantity here, fxx fyy minus fxy squared is greater than 0. So we have to calculate this quantity. We multiply the two, same partials, and then we subtract the mixed partials squared. This is really, again, remember, this is fxy times fyx, but according to Euler's theorem, they will always be the same, provided they're well behaved. And so we can just kind of square one of them. Less work. We only need to calculate 3 out of the 4 instead of just, all 4 of them, which is nice. F is a local min at AB if the second partial, double partial with x, is greater than 0. And this quantity again, minus fxy squared, is greater than 0. So there's kind of two things we need to check. We need to check what the the second derivative only in respect to x is positive or negative. And then we look at this strange quantity here to see if it's positive or not. If it is positive, this strange quantity, then we either have a local max or minimum, then we then check f double x to see which one it is. If it's less than 0, it's a local max. If it's greater than 0, it's a local min. I like to always think of it as kind of the opposite of what you'd expect. Max, we think big, but it's less. Min, we think small, but it's greater than. F has a saddle point, this new guy here, at AB, if we don't need to worry about the second double x partial, but we look at this quantity again, and we get a saddle point if it's less than 0. If that's a negative quantity, it's a saddle point. If we end up with our fun quantity is exactly equal to 0, it's inconclusive. We need to find another test. Maybe we'll look at the structure more carefully and see what kind of point it is. But hopefully it ends up being in one of these first 3 categories, and we can classify that point like we want. Really, this quantity here, it comes from the determinant of a matrix of the partials. So if we build the matrix, we put the x derivatives first in the first row. We do the y derivatives first in the second row. and then we take the determinant. Take the first diagonal here, fxx times fyy, subtract the cross across the product across the other diagonal, fxy squared. Remember, these are always going to be equal. This quantity here, we take it using a determinant, but itself is called the discriminant. So for hereafter, I will call the strange quantity the discriminant. So now we have our second derivative test. Let's try it out. Let's take a little function here. We're going to have xy minus x squared minus y squared minus 2x minus 2y plus 4. I couldn't begin to tell you what this looks like off the top of my head. You can go ahead and plug it into Desmos or something like that if you're curious. But the point is, we don't need to know what it looks like. We have our first and second derivative test that will help us figure out where these special values are going to be. So let's first, by taking our partials, we got to find our first and our second partials. So we do our x1. We're going to get y minus 2x minus 2. And for our y derivative, x is now the constant, we're going to get x minus 2y minus 2. If I take the second x partial of the x derivative, I'm going to get minus 2. F of xy is equal to f of yx. That's just going to be equal to 1. See, I got a y here, so that's just going to be 1. Everything else is a constant with respect to y. Same thing over here. If I take the y derivative, I take the partial with respect to x. Everything except this x is constant, so we just get another 1. And then finally, fyy equals negative 2. First things first, we should set these derivatives equal to 0. We'll need to solve the system of equations to see where this point AB actually is. So I can get y minus 2x minus 2 equals 0. I get y is equal to 2x plus 2. I can plug that in to the y derivative, setting it equal to 0, and I will get x minus 4x minus 4 minus 2 equals 0. So we get something like negative 6, negative 3x equals 0, or x will have to be equal to negative 2. If x is equal to negative 2, then that means that y will also be equal to negative 2. Plugging that back into my expression for y, I get negative 4 plus 2 equals negative 2. So at the point negative 2, there should be an extreme point. What kind of extreme point is it? Well, now we enter the second derivative test. It's nice here, and this will not always be the case, but our second partials are just constants. If they were not constants, we would plug in our values for x and y to kind of make them constants. But, for all x and y, whatever point we're at, the second partials have this structure, which is kind of nice. So we put it in. Negative 2 there, negative 2 for our double y, and then we get 1 and 1 on the off diagonal. We take the discriminant, we get negative 2 and negative 2, gets us positive 4 minus 1 equals 3. So we have a positive discriminant here. We consult our chart up here for the second derivative test. So it's either going to be a local max or a local min because the discriminant was positive. I go and look at my second x, and it is negative. So that means that of the possible choices here, fxx is negative, it's negative 2, that means we have a local max. So fxx is less than 0, our discriminant is greater than 0, so that plugs us right into a local maximum. We know where the local maximum is. It's at negative 2, negative 2. We know that it is a local maximum by our second derivative test. If we wanted to know what that actual value was, we can just go plug that back into the original function now, just like we would in 1D. When we find where the critical point occurs, we want to know what value the function actually assumes. So negative 2 times negative 2 is 4, minus negative 2 squared is 4, minus another 4. We get plus 4, another plus 4, and then it's a lot of 4s there. So of these 4s, I have 1, 2, 3, 4 positive, minus 2 of them are negative, so that's going to be just equal to 8. Whew. So after all is said and done, we've shown with our first derivative test, setting our first partials each equal to 0 and solving the resulting system of equations, that we get that the critical point is at negative 2, negative 2. We use the second derivative test to classify what kind of point it is, and then we can finally say that the actual value that the function has is 8. We take a step in any direction from negative 2, negative 2 on that function landscape, and we will end up at less than 8 because it's a local maximum. So that's our general strategy there. If you end up with a function that has multiple solutions, you want to use all the possible permutations. So I'm not going to go through it all the way, but just to show an example. If multiple solutions, use all possible permutations. So for example, if I have f equals x cubed plus y cubed plus 3x squared minus 3y squared minus 8. When I take the derivative, I'm going to get 3x squared plus 3y squared plus, nope, just kidding. We're only taking respect to x, 6x. So I get 3x squared plus 6x. The y derivative is going to be symmetric. It's going to be 3y squared minus 6y. So if we work this out, I can factor out a 3x from each of those terms and get an x plus 2 equals 0. And over here, I can factor out a 3y and get y minus 2 equals 0. So that tells me that x could be 0 and negative 2, whereas y can be 0 and positive 2. We would need to look at all these possibilities, 0, 0, 0, and 2, negative 2 and 0, negative 2 and 2, and see what sorts of things arise from that. So just to be aware, if you have, higher order functions, the derivatives themselves might be quadratic, they might be cubic, they might have multiple solutions. You'll need to figure out, how all those possibilities work together. Just to spoil for you, left as an exercise for the viewer. The origin 0, 0 ends up being a saddle. 0, 2 ends up being a local min. Negative 2, 0 ends up being a max. And negative 2, 2 ends up being a saddle point. So you can check that on your own time. This is all good, but sometimes there might be a region where there is no local maximum, minimum, or saddle points, but there still might be an extreme values. If we have a finite region of space, that bounded region may actually assume its maximum values as an absolute extreme point on the actual boundary itself. So if you are given a region, you do want to use your first and second derivative test to find the interior critical point. So find interior critical points using first and second derivative tests. One thing to look out for is when you use the first and second derivative test, you're looking at the function over all of its possible values. If you have a finite region, you want to make sure that the extreme values that you found actually live inside that region. It's possible you could find something that you don't care about. So just make sure that you work within the context of the given region. You're going to find boundary points with local and maxima and minima. And then you're going to kind of cross-reference these two lists with each other to find the greatest and least among them. So here's like all the points that could be critical or could be some largest point on that boundary. The largest absolute maximum and the absolute minimum are going to be the greatest and least among them. Compare these lists to find greatest and least among them. So we're looking for the overall greatest or smallest points within a region. So here's our nice region. Well, we'll see how nice it is in a second. It's a triangle. It is defined by the lines y equals 0, so the x-axis rather, x equals 0, it's the y-axis, and the line y equals 9 minus x. So that means we have this endpoint here, 0, 9. We have the origin, 0, 0. And then we have this point here, the x-intercept. We can set y equal to 0, and this is going to be 9, 0, in other words. Right. So we're going to look at the function f of x and y equals 2 plus 2x plus 2y minus x squared minus xy on this triangular region. So this function is doing some kind of wavy thing inside this triangle. We're going to figure out what the largest and smallest points are in this specific region. So we start by finding the interior critical points. We're going to look at our first derivative. And with respect to x, we're going to get 2 minus 2x equals 0. And with respect to y, we're going to get 2 minus 2y equals to 0. If we solve these, we're going to get x equals 1 and y equals 1. So we have a critical point at the point 1, 1, somewhere inside of our region. So that critical point lives in our region. We can evaluate what that function actually is. We can do f of 1, 1. So we get 2 plus 2 plus 2 minus 1 minus 1. So that'll be 4, 6 minus 2 gives us 4. So at this critical point, the function assumes a value of 4. Now, we're going to look along our boundaries. One thing we'll want to check is the actual endpoints of the function itself. So we want to look at the values f of 0, 0. Basically, at the origin, all x and y's become 0, and we're left with just 2. So we'll get 2. We can look at the point 0, comma 9. So x is 0, y is 9. We'll get 2 plus 0 plus 18 minus 0 minus 81, which will evaluate to negative 61. This is a clear front runner for local minimum so far. And then finally at the point f 9, 0, it's symmetric, so it should be the same. We get 2 plus 18 minus or plus 0 minus 81 minus 0. So that should be negative 61 again. So this checks the interior. This checks the endpoints. Next, we need to make sure that, whatever this function is doing, there could be a higher and low value along the actual boundaries themselves. So what we need to do is we need to look at those actual boundaries. We get for x equals 0. So we're going to turn this 2D shape into basically a 1D function along this leftmost boundary where the x coordinate is 0. The new function we get in terms of that. So we'll call this f of 0, comma, y. This is going to be 2 plus 2y minus y squared. If we take the derivative along that boundary, we're going to get 2 minus 2y equals 0, as we do for 1D functions. And hey, this is kind of just the first, our partial over here. So we get y equals 1. Now we need to look at the point x of 0 and 1. 0 and 1. So we plug that in the original function, or really just kind of this endpoint here. We'll get 2 plus 2 minus 1 is 3. So that one's not especially standout point either. Now we'll do y equal 0. So we're looking at f of x, comma 0. We'll get 2 plus 2x minus x squared. We take the derivative df dx. 2 minus 2x. Hey, that happens when x is equal to 1. Turns out we plug that back into our function. We get 2 plus 2 minus 1 is another 3. So this gives us f of 1 comma 0 is 3. Finally, we need to check this last boundary. This is the trickiest one. So y is equal to 9 minus x. X is just going to be equal to x. So we're going to look at f of x, comma 9 minus x. Everywhere we see a y, we're going to replace it with the formula for the boundary, 9 minus x. So that's going to be equal to 2 plus 2x plus 2 times 9 minus x squared minus 9 minus x squared. We can take the derivative of this. We're going to get 2 minus 2, so the 2 distributes there, minus 2x minus 2 9 minus x times minus 1 with the chain rule there. So we'll get 0, negative 2x, the minus signs cancel, plus 18 minus 2x equal 0. So here we'll find that x is going to be equal to 18 over 4, or about 4.5. Or 9 halves, another way to say that. If I plug that back in, that means that x is equal to 9 halves. So we have x is 9 halves. 9 minus 9 halves. Well, this is 8. Sorry. We're going to subtract x there. That will be 18 halves minus 9 halves. So yes, this is the function evaluated at 9 halves, 9 halves. You can plug that in to the original function or see what you get. 9 halves, 9 halves. 2 plus, luckily the 2's here are going to cancel out the halves, so we get 9 plus another 9 minus 9 halves. We're going to get 81 fourths minus 81 fourths. So this will be 20 minus 162 fourths, which evaluates to, if you simplify this, you'll get negative 41 halves. So that's a pretty small negative value, but it's still not as negative as the negative 61s. So we look at all these different values we have. 4, 2, negative 61, 3, another 3. this crazy one where we got negative 42 of 1 over 2, and we find that the absolute maximums occur at the endpoints where the function assumes a value of negative 61, and the absolute maximum within this boundary is the interior point 1, 1, where the function assumes 4. So it gets a maximum value of 4 and a absolute minimum value of negative 61. It gets pretty negative pretty fast within this triangle if you step away from this island at 1, 1. So that's a lot of work. But to summarize, you use your first derivative test to figure out where the critical points in the interior are, and then you look at the endpoints, and then you evaluate each boundary separately just by plugging in what x and y are on that boundary. And that does it for extreme points.